In part one, we found out amazingly that it is correct to play the tape of the expanding universe backwards all the way back to just 380,000 years after the beginning, time t equals 0. Because at that time, we saw that the universe was 3,000 degrees Kelvin or centigrade scale. And the proof, the actual evidence that the universe really was in that state is the cosmic microwave background. So that's our first piece of evidence that yes, the Big Bang is real. Today, I'd say drunk with that success, we're going to go even way further back in time. Let's keep on playing that tape backwards to a time when the universe was only 1 second old. So that means not just 3,000 degrees, but the universe was 100 billion degrees. It was filled with, the microwave background had not become just visible radiation, it was gamma rays. Very high energy photons zooming around in a very dense sea of fundamental particles at this temperature. That is about the temperature. In fact, it's actually hotter than the temperature experienced inside the center of a supernova explosion. And you know, a lot of interesting things can happen in the center of a supernova explosion. This is going to be a little bit different because the universe, I'm talking about the entire universe, was somewhat less dense than a supernova. But it does raise the possibility, which is a reality now, that we're going to be able to make predictions about thermonuclear fusion reactions that were taking place throughout the entire universe, not just in one location, like the center of a star, starting at 1 second. We'll see why I start there in a minute. That's the first time that the universe had really cooled off enough, only 100 billion degrees, to where you could actually have things such as protons and neutrons being stable. Now, as soon as you have that, then you should be thinking, what's to stop them from colliding and sticking together to make a proton plus a neutron, which of course is heavy hydrogen. That's the nucleus of deuterium. Seems like that would be fairly easy to happen, in fact, at that temperature, and you would be right. By the way, that's not exactly what happens in the sun, is it? Because there aren't free neutrons wandering around. But there were free neutrons, as we'll see, wandering around throughout the entire universe, just looking to hook up with a proton to make deuterium. Here's the problem. So yes, that would have happened, and it started happening fairly big time at 1 second after the Big Bang. The problem with this is that the deuterium nucleus in particular is rather fragile as atomic nuclei go. What I mean by that is that at a high temperature, the collisions are so violent, so high energy, such high speeds, that corresponds to 10 to 11 degrees, that the instant that a proton-neutron will come together to make a deuterium nucleus, another collision will come along with some other very high energy particle or a gamma ray and break them apart. It's a little bit like an analogous reason to why molecules can't exist at very high temperatures, and even at higher temperatures, even stable atoms can't exist. The energy holding them together is just not enough compared to the energy of everything that's moving around at 100 billion degrees. So pretty much the instant that a deuterium nucleus forms from a proton and a neutron, a split second, a millionth of a second later, it's broken apart and you just have the proton and the neutron again. In other words, it's trying. The universe would love to make something more complicated than just protons and neutrons and electrons. It would like to try to make the first step in nuclear fusion to something more interesting and advanced, but it's stuck because the best it can do, the simplest thing it can do, deuterium, is so unstable that it won't survive. And so the universe really can do nothing. It's just on pause, waiting for the expansion to continue, waiting for time to pass. The clock is ticking now, 1 second, 2, 3, 4, as the temperatures are going down, waiting for what? Waiting for about a minute or so for the collisions to not be so violent, the energies of the gamma rays to not be so high, that deuterium can survive, actually, and then do some more interesting nuclear fusion reactions if it can survive just a split second after it's formed and not be busted apart. So this period when the universe is kind of doing nothing for a while. It hasn't had much time to do anything, but from 1 second for at least another minute, this is called the deuterium bottleneck, because we have to wait for the universe to cool down by about another factor of 10. So what happens then? Then things get pretty interesting. By the way, let's look at this. The question of, well, where did those neutrons come from? The neutrons came from what the universe was doing even before it was 1 second old. In other words, when it was above 100 billion degrees. So these are extremely high energy reactions involving our old friend, the weak nuclear force that we don't always pay that much attention to, turns out to have played a crucial role when the universe was less than 1 second old. And that crucial role is, you may recall, that in a certain kind of weak nuclear force reaction, that means it has a fairly low probability of happening. You need a very high density of particles to have it happen. It helps to have a very high temperature, and it involves neutrinos, those ghostly particles. Anyway, in one of these reactions, we've seen this happen actually in the sun too, you can actually have a proton converting itself into a neutron. Oops, we have to preserve total electric charge. Proton would be a plus charge, so you could convert it to a neutron plus a positron. That's a positively charged electron, the antiparticle electron. And of course, a neutron could also convert back. If a neutron happens to find a positron, it could convert back through these weak nuclear force reactions into a proton. So at earlier times in the universe, there were protons and neutrons going back and forth between each other. They're not that different particles, except for the electric charge. And then that stopped at about 1 second. That's where I picked up the story here. Again, so far this is just a story. You're waiting patiently, I know, for the actual evidence, observational data that shows that I'm just not making this stuff up because we're crazy. So if this is correct, though, that neutrons and protons were switching back and forth from each other, then we have a statistical idea of how many protons there were as the universe got up to about 1 second of age, and then stopped doing these weak nuclear exchanges. So at that point, the protons outnumbered the neutrons, and then we had to sit around and wait for a minute or two. Free neutrons, are unstable. They can't exist by themselves. They have a half-life of about 11 minutes. Which has actually been measured in a laboratory. So if you wait a few minutes, the neutrons will naturally, some of them will naturally decay back into protons. So we started out with more protons, but an interesting contamination minority of neutrons. And then you wait a few minutes and there's even less neutrons. Most of the nuclear particles now are going to be protons. But then, so that's where we are up to, I'd say, about a minute or so. And then the temperatures drop below only 10 billion degrees, and now we've passed the deuterium bottleneck. Now deuterium can actually survive. And then it can go on and have, since it doesn't just split apart and bust it up as soon as it forms, it can enter into more complicated thermonuclear fusion reactions. And the one that it's most likely to do is to either capture, well, it's probably going to capture another proton at some point, and then maybe another one or a neutron. And there's a number of different reactions which I don't want to go into. The bottom line is that as soon as the deuterium bottleneck is broken by the universe cooling off, allowing deuterium to survive, the deuterium will very rapidly react by taking protons and neutrons to make helium. That is a much more stable atomic nucleus, and you all remember that has 2 of these protons. We're color coding it here for their +1 charges, and then 2 neutrons, which are gray there. And so what is statistically actually very likely to happen is, in very short order, all the deuteriums, all the heavy hydrogens, in fact, anything that has any neutrons at all is going to end up through a series of reactions incorporating all the neutrons into helium. So pretty much in a very short amount of time, all the neutrons that were around at that point in the Big Bang go into heliums. And of course, we know the proportions there. It takes 2 neutrons and 2 of the protons to make 1 helium. Now, I've actually put in the correct numbers in this artist's conception here. There's all the protons. Nice of them to line up like that in the Big Bang. And statistically, there was about 7 protons for every neutron, or 14 protons for every pair of neutrons by the time that the deuterium bottleneck was broken and all of the helium nucleosynthesis starts happening with a vengeance. And so you can see then just by the numbers here that we're going to take 2 of the protons and 2 of the that were there, combine those with the neutrons to get 1 helium, leaving behind a leftover of 12 protons that can't find a dance partner. They can't undergo those easier nuclear fusion reactions, and they don't really have time to, and they don't have the energy and the temperature to do anything else. So these 12 protons got left out, and all they're going to end up 380,000 years later, these are going to end up combining with electrons and making hydrogen atoms, which are still out there today, although they've largely been ionized again by new stars. But anyway, these hydrogens should still be around in the universe all over. And for every 12 of them, this is a prediction, if these calculations are correct. If we really are describing the first few minutes of the Big Bang, the prediction is at the end of the first few minutes, there should be 1 helium nucleus, leading to a helium atom later on, for 12 hydrogens, 12 to 1, which if you go by a mass ratio, since this particle has 4 times the mass of these hydrogens, then the mass ratio in the universe should be about 3 to 1. In other words, the material that came out of the Big Bang, this is a prediction now, this is an actual quantitative prediction, should consist of 25% by mass helium and 75% by mass hydrogen. You can go out and observe that. This is a prediction of what the primordial abundance of helium compared to hydrogen is, if only you work hard enough and you can find some truly primordial. What I mean by primordial, I mean leftover, untouched, uncontaminated from the Big Bang, not having gone through any further, more complicated generations of nucleosynthesis. In other words, I need to find some gas that has not made stars yet at all. It's just left over from the Big Bang. That's not trivial to find. A lot of gas has been through the center of a star, as we found. It's experienced more complicated fusion reactions to produce carbon and all those other things. But you can, if you look hard, find very young primordial galaxies which have gas clouds which seem to be almost pristine. They have almost no heavy elements produced at all. They've hardly formed any stars at all. Okay, these galaxies got a pretty late start on things, as they're barely galaxies at all. But some of these have been measured in great detail. And you find that every single one of them basically always has pretty much the same amount of helium, 25% by mass. Not 1/3. Not 1/5, not 1/8, 1/10, whatever, not some random number, but the actual number that's predicted by the fusion reactions predicted to take place during the first 2 or 3 minutes of the Big Bang. Wow. So there's my second piece of spectacular evidence, which was sought in the 60s and 70s by people thinking about taking it seriously. I think after the cosmic microwave background, people had to really start taking it seriously. Yeah, we can probably extrapolate the expanding universe back to an outrageously high temperature where these fusion reactions took place, and we can compare. This is our second piece of evidence. Second thing that tells me, where's the evidence? That's the evidence. The cosmic primordial abundance of helium compared to hydrogen, coming in just about what was predicted. But there's actually more here. Now, I just want to mention this. I got a complicated graph that needs a lot of explanation in a second here. What about more nuclear fusion reactions? Now that we've got helium, you know that can do some interesting fusion reactions as well. There's protons around, there's heliums around. Why can't they just combine and fuse and make some other products of fusion? during the next minute or two after the first 3 minutes had formed the helium. Well, there's a problem. We're kind of running out of time, and we're running out of density. Now, see, all of these fusion reactions that make the helium are all done by the time the universe has cooled off to about 10 million degrees. That's done after about 3 minutes there, 200 seconds. And so, for example, what would be the simplest thing you think of? Well, I got a helium now. Let's just add one proton to it, helium plus hydrogen. Or if you want to get more fancy, I got a number of heliums. Let's just stick 2 heliums together. In the first case, you get helium that's 4 plus proton is 1. That would make an atomic nucleus of mass 5 nuclear particles. Or 2 heliums would make an atomic nucleus of mass 8. Look it up in your periodic table of the elements. What is the atom with an atomic nucleus, an atomic weight of 5? What is the atom in the periodic table of the elements that has a nucleus of 8 atomic particles, protons and neutrons? Trick question. There is no stable atomic nucleus of mass 5 or mass 8. They don't exist for various random reasons. They just can't exist. As soon as the helium would stick together, the proton will break apart again. 2 heliums stick together, it breaks apart again. We actually already saw this in the center of the sun. And the sun was stuck with the same problem. The bottleneck of no stable nucleus of 5 atomic masses, no stable nucleus of 8 nuclear particles existing. And the sun came up with a very special, wonderful, essential to us and our existence solution. What was the solution for the sun? Have to wait around for a rare triple collision. 3 things together. I really emphasize that, I think, on the exam, how improbable that is. It's hard enough to get 2 to come together, but at the same second, same instant those 2 come together, that same nanosecond, a third one comes. Well, then you get the triple alpha reaction, which we're very fortunate happens much more, is much more likely than you would have thought, only at high density. But now the universe as a whole is much, much less dense in the center of the sun. So those triple reactions not going to happen. There is no triple alpha that's going to come along and produce carbon in the Big Bang. Couldn't happen. The Big Bang gets stuck once it has hydrogen and helium, and it cannot get past it. That's why I kept emphasizing throughout the course, we absolutely know that any of the heavier elements, such as carbon, could not have come from the Big Bang. We absolutely had to have stars to go through their later phases of their evolution to produce those heavier elements. However, most of the hydrogen and helium that you still see in the universe, quite a bit of that is still the original, leftover, primordial, hydrogen, helium, all produced in the first 3 minutes. Now, carbon, nitrogen, oxygen, all those other things that we love as biological creatures and so on, yes, all of that did have to get produced later in these more advanced nuclear fusion reactions in the high-density cores of stars. But the basic building blocks were there after the first 3 minutes. But there's more here, and what is that? Any other kinds of reactions? Well, actually, we don't need any more reactions really here. Let's just look back at the reaction I was talking about before. There wasn't much time. Was there really time for all of those heavy hydrogens, all of those deuterium nuclei to find partners and get another proton, get another neutron? Was there time for all of them to convert all of the protons and all of the neutrons into heliums? It was touch and go. Depends. Depends on how rapidly the nuclear fusion reactions were able to take place during those first 3 minutes. And it's not absolutely guaranteed. The rate at which those fusion reactions could use up the deuterium depends on how many available targets, how many particles they were, how densely packed they were. So it really depends on the universe's density of hydrogen and helium, or the universe's density of protons and neutrons. If the universe today had a pretty high density, then it had a pretty high density of normal matter, protons and neutrons, during the Big Bang. And then there would have been so many of these collisions that almost all of deuteriums would have gone on to the more advanced reactions and would have all ended up incorporated in heliums. But if we, as it turns out, live in a rather relatively low density of normal matter, that's protons and neutrons, universe, then some of the deuteriums didn't have time, just didn't get hit by another proton or neutron, so they did not progress to helium. So that's what I'm trying to show you in this next. It's a complicated slide here. I do want to make one mention. So this was worked out actually, I think, in the 70s. And of course, we had to understand what these nuclear reaction rates were, as in some cases measured experimentally. And I just want to mention one of the pioneers in this field, David Schramm, an amazing scientist who worked on a lot of this stuff. It's just a dynamo of a person, and he tragically died way too early, flying his single-engine plane to Aspen, something he loved to do. And I just want to say, Dave, your work lives on, is not forgotten. I'm going to tell the students about that right now. What Dave and other collaborators realized is, if you could measure how much of this rare leftover trace of heavy hydrogen there is. Most of it is normal hydrogen, and the rest of it all got incorporated in helium, but a little trace might remain. If you could measure that little trace of heavy hydrogen, you could actually infer what the universe density of normal matter is. The question is, we have to find this heavy leftover isotope of hydrogen, deuterium, proton plus neutron here. All right, so let's look at this graph. Here is a graph. Now this is something we're trying to figure out. What is the density of normal matter? Protons, neutrons, electrons, they don't count for much mass there. What is the density of them? Now we're going to compare this to the critical density that would be high enough to stop the expansion of the universe. So that would be a very high density universe, and here's an almost completely empty universe down here. It's a factor 10, that's a factor of 1,000 there. On the vertical axis, I mostly want you to look at the red line. The red line here, again, this is a logarithmic axis, shows what proportion of the hydrogen would be left in a heavy hydrogen form after the first 3 minutes of the Big Bang. How much deuterium or heavy hydrogen could survive? And you can see the survival curve. It starts out, there's quite a bit of it, 1%. But then as you get to a more and more dense universe, there were more and more frequent collisions, more and more frequent reactions, getting the deuterium to fully incorporate into helium. And so it's very easy, in fact, to have almost no heavy hydrogen left in the universe at all. That's 1 part in 10,000. There's a part in a million, a part in 100 million, a part in 10 billion. So it would have been easy for all of the heavy hydrogen to basically be gone. But it's not. Again, another experiment that you want to do, and this is even harder than the measurement, we want to find a primordial gas. We want to find primordial gas now, and we already confirmed that it's about 1/4 by mass helium. Now I want to do a much more difficult observation. This is a super challenge. Can you tell me how much is contaminated with heavy hydrogens compared to the normal hydrogens, which just has 1 proton? The observations are very difficult to do. I'll tell you in office hours. The great saga of doing this, we had to look at very thin gas clouds of primordial gas that are so far away that you could only even tell that they're there because they absorb quasar light at a very high distance. It's a beautiful technique and a beautiful, audacious observational success. The answer, I'll just tell you right now, and then you can read it off the graph. The answer is that for every normal hydrogen with 1 proton, there's about 1/40,000th of them are actually heavy hydrogens. So there's 40,000 normal hydrogens for 1 heavy hydrogen, 40,000 to 1. In fact, that is approximately the ratio in seawater. And if you go to a lot of trouble, you can separate out the heavy water in seawater anyway, and you might actually use that for certain things. Heavy water, as we've seen, is very useful and valuable. Anyway, and it's very rare. That's why this stuff costs so much. Only 1 hydrogen out of 40,000. Let's look at the graph here. Going down from 100th, 1,000th, 1/10,000th. Whoa! Right there, where my cursor is here, is the observed range. 40,000 normal hydrogens for one deuterium there. And that tells you an amazing thing. Just read down the graph here, looking down. To get that amount of surviving deuterium, heavy hydrogen, from the Big Bang, to have it today in these primordial gas clouds, we could not have had too many collisions or too many reactions with protons and neutrons. There couldn't have been too much of it. In fact, the universe must have had only 4% of its critical density in the form of normal matter, like what we're made of. You got that? So the normal matter that we're made of is a pretty small fraction. It's not zero, but it's a pretty small fraction of the amount of mass that it would actually take to close the universe. And now here's the big dramatic point, though. We've already learned from other cosmological observations we talk about in another lecture in the course, that the total amount of gravitational matter in the universe is actually almost 1/3 of the critical density. What does that immediately tell you? The last line here, the bottom line on the slide. The great majority of mass in the universe must not be made of normal matter that can interact with deuteriums. It's not made of protons, neutrons, and electrons. It must be made of some exotic form of material that only has weak interactions with other matter. Could be neutrinos, weakly interacting massive particles. And so not only is that a thing, we've already seen that that's a thing from the dark matter problem. Not only is this matter not making any light, it's not interacting with normal matter at all, it's not even made of normal matter, and it's the majority of everything in the universe. This is an incredible shock to physicists, to everybody in science, that we've only been studying what we're made of. We've only been studying the 4%, not the other 30%. We've only been looking at less than 1/7 of all the mass that's there because we frankly have no idea what the other 6/7 of the universe is, except that it's something much more exotic than what we're made of. So that's kind of a slap in the face to Copernicus, isn't it? We're not even actually made up of the most typical stuff that the mass of the universe is typically made of, and we haven't even discovered. It's probably not even yet known to science. It's some kind of weakly interacting particles, and all they seem to do, they're not doing any weak interactions now because the densities and temperatures are too low, probably. Maybe they decay occasionally, although they must live for a really long time. All they have is mass. That's all they do is they create gravity. Oh, but I am so glad. I am so thankful that they do create gravity, because their gravity, which dominates the gravity of the universe, was what built all of the structures, all of the overdensities of the universe, such as the first clusters of galaxies, the first stars in those galaxies. Well, that formed later. In other words, the possibility of ever having stars and planets in a system like our solar system absolutely required all of this dark matter to produce enough gravity to destabilize the universe and cause regions of it to collapse and make us. So thank you, dark matter. We still wonder what you are. We're trying like crazy to figure out what you are, but we are very grateful for you allowing the universe to create abodes for life that we can enjoy. Thank you very much, dark matter.